So hopefully everyone was able to watch last week's video on Waterside heating systems. That was the one that I had to pre-record because Waterside cooling systems share a lot of the same systemic DNA, let's call it. So this does kind of piggyback on Waterside systems, but is really dealing with a lot of the same concepts. So we've looked at Waterside heating. Now we're going to shift gears, look at Waterside cooling systems. Same basic idea. We're still pumping water out into our building, out to a bunch of coils that we use to condition our air in the building, except now instead of using hot water, we're using cold water that are going to cool a bunch of air streams throughout the building, as opposed to heat them. Instead of a boiler, which we use to make hot water, now we're going to have what's called a chiller. And I've mentioned chillers several times in this class so far, but up until now, you might not have really known what I meant by that term. Here's a basic chilled water cooling system. And at a glance, you're probably going to notice that, hey, this looks very, very similar to a hot water system. In this case, we have a chiller, which is going to take warm-ish water and cool it down. It will chill it and then send it back out into the system. We have our chilled water supply, which is going to be around 45 degrees. So that is what is leaving the chiller. That's what we are cooling down our water to. This gets pumped out to a number of chilled water coils out in our air handling units. We run the chilled water through the coil, which pulls heat from the airstream that's going over the coil. So we end up with cooler air on the outlet of this air handling unit. And then it's going to leave the coil a little bit warmer because it's absorbed heat from the airstream. All of the chilled water returns from all of our equipment out in the building is going to come back now into our chiller. And our return is going to be about 10 degrees warmer than whatever our supply is. So if we're sending it out around 45 degrees, the return will come back at around 55. That triangle in the circle, again, that's a chilled water pump that represents diagrammatically a pump in our system with the direction of the triangle indicating the flow direction. We end up back at the chiller where we chill it down again and then we send it back out, and you just have this cycle. Fundamentally, this isn't very different than a hot water system. It's just we're moving chilled water instead of hot water. On the coil side, just like hot water, it's very similar. So we have our copper piping, we have aluminum fins to help make that heat transfer happen. We're going to pump in our cold chilled water supply at around 45 degrees. Hot air goes in, cold air comes out, and then our water comes out about 10 degrees warmer. So this coil is constructed the same exact way as it is for a heating coil. There's really no difference at all. The only difference you might have is to get the heat transfer we need, we might need more passes through the coil or more aluminum fins per inch of coil or something like that. So we have our copper tubing fused to aluminum fins. It's all the same. Our driving equation is Q equals 500 times GPM times the delta T of our water. Q being our heat transfer in BTU per hour. GPM is our water flow in gallons per minute. And then the delta T is the temperature of our water going in versus coming out. And that should look very familiar because that's the same equation we used on the heating side. So same exact equation. And that makes sense because a coil, all that really knows is it's losing energy or gaining energy, depending on the application, heating or cooling. It just knows energy is either leaving the coil or it's entering the coil. And so fundamentally, the equation doesn't change. It's just a matter of which direction the heat transfer is occurring. But one difference on the cooling side is the air side heat transfer component, because remember, we're going to have a heat transfer component on the fluid, whether that's hot water or chilled water, and there will be a corresponding equal amount of heat transfer on the air side. And those two have to equal. Whatever is entering the water has to be leaving the air, or vice versa. But the difference in cooling is the air side has both a sensible and a latent component. So you'll have to think back to when we were talking about the HVAC introduction lecture and how that gets split, and how the sensible cooling is all about changing the temperature of the air. The latent is all about condensing water out of the air. And that's not something we see on the heating side. This is unique to cooling. But that's only on the air side of the heat transfer process. The water side, if we're looking at the coil and the fluid that's moving through the coil, that doesn't differentiate between sensible and latent. All it just sees is cooling. It's just all cooling. So for example, you could have 100,000 BTUs per hour of total cooling at the coil side. So that's how much energy the fluid is extracting out of the airstream to cool it down. And on the air side, that could be split between 80,000 on the sensible and 20,000 on the latent. But as far as the coil is concerned, it's all cooling. It doesn't know what's sensible and what's latent, because on the water side, there is no latent load. We're not changing state, which that's what's going on with the latent load. We're taking water vapor and condensing it. In summary, on cooling coils, we have our driving equation. And as a reminder, our sensible air heat transfer equation is 1.08 times CFM times the delta T of the air. The latent load of the air would be 4,725 times CFM times the delta in the humidity of the air, in versus out. And then the delta Q on our water is going to be equal to the delta Q sensible plus the delta Q latent on the air side. So this is kind of a review of multiple previous lectures where we've talked about water side heat transfer and air side heat transfer. So how do we make this work? There are a couple different methods that we can use. If we're going to chill the water, then we have to remove heat from the space or from our building, and then we have to dump it somewhere. Because remember, air conditioners, they don't create cold. They're just moving heat energy from one place to another. And that whole methodology doesn't change with chillers. So think back to a standard DX air conditioner and how we're dumping heat to the outside. So if you went to an air conditioning unit sitting outside and you put your hand over the fan that's blowing air out of the air conditioner, that air is going to be very, very hot. Not hot enough to hurt you or anything, but it's going to be noticeably hotter than the surrounding air, outside. And that's because the system is dumping heat into that air and then pushing it outside. Chillers fundamentally are doing the same thing. And in a chilled water system, generally speaking, There are some caveats and specific changes to this, but fundamentally, there are typically two ways to reject heat in a chilled water system. The first method, and this is the, using air quotes, easy method, would be to use an air source chiller. I'll have a graphic here in a second that will help illustrate this, but the chiller that we're using to chill down our water stream sits outside of the building, and it has to sit outside the building. And then we're going to use a standard DX refrigeration cycle that will take heat from the chilled water and then dump that heat outside. So this should sound very similar to an air conditioner. We're taking heat from the water and then dumping it outside. Our water's coming into the chiller a little warm because it's absorbed heat from the building around 55 degrees. And then we reject that to the outside, and then it'll leave the chiller, go back into the building at a colder temperature, and then just keep going through that cycle. Here's an example of what a bunch of air source chillers look like. And this would be for a pretty good sized system. Most commercial buildings that have a chilled water system probably just have one chiller, and that's it. So this would be a much larger system where they have, what's that, 9 chillers? And even then, these look to be a little bit modular. You can kind of see a separating line going down the middle where you could basically imagine cutting each of these in half. So in theory, this could be more like 18 chillers. So we have our chilled water supply and return. So I don't know which one is which, but one is going into the chillers and one is leaving the chillers. We have our condenser coils that are rejecting that refrigerant heat into the condenser air. We have our condenser fans on top, and that's, like I was saying earlier, if you were to put your hand over that fan, it would feel very warm because that's taking in outside air through the side of the coil where we're running our hot refrigerant, and then that air is going to leave warmer. And that's your building heat that we're rejecting outside. With an air source chiller, the evaporator and the condenser, it's all packaged into the chiller. When we were talking about heat pumps and air conditioners before, we talked about how you usually have an indoor unit and an outdoor unit, and they're piped together. In an air source chiller, this is all packaged in that box we were just looking at. And this would be a water to air heat transfer process. The reason they call it an air source chiller is because we're taking energy from the chilled water and putting that directly into the outside air of just the ambient air of the building. So the air, the outside air, is our heat sink. That's where we are rejecting the heat. So that's where this term air source chiller comes from. The efficiency of our chiller is going to be driven by our dry bulb outside air temperature. If it's a little bit colder outside, it's easier to reject that heat, and that's going to lead to less energy use at the chiller. But if we have a higher outside air temperature, then it's harder to reject that heat to air that's already hot, and our chiller is going to have to work harder. So the dry bulb outside air temperature is the primary driver on what's driving our efficiency. A little sketch to kind of show what this looks like. If it's not clear enough already, we have our air source chiller that's going to be on the roof or the ground, has to be outside, sending our chilled water supply through our chilled water pump that's going to go out into the building to all of our chilled water cooling coils. Then it'll come back a little bit warmer, go back into the chiller where it ultimately rejects that heat outside. So that's method one. That's what I call the easy way to do it. Because in this scenario, you only have to worry about one piece of equipment. You just have to buy the right chiller for whatever job you're doing, and everything comes packaged in that chiller. Everything you need is going to be in this box right here. But that brings us to the second method, which is a water source chiller. So before we were talking about an air source system, this would be a water source chiller with a cooling tower, or could also be called a fluid cooler. There are some differences between a cooling tower and a fluid cooler, but that's not something I'm going to get into for this class. In this scenario, the chiller actually sits inside of the building versus an air source chiller, which sits outside of the building. First, our heat energy is going to be pulled out of our chilled water stream. That part's not any different. We're still coming back with warmish chilled water, and then we're going to be pulling that energy from our chilled water stream. But the difference here is we're then going to dump that into a secondary water stream, which is called condenser water. So on one side of our chiller, we have chilled water. On the other side of our chiller, we have condenser water. So now the chiller, which remember is inside the building, that's not dumping heat directly to the outside. Now we have a water to water heat transfer process. It's not a water to air heat transfer process. We're still using a DX refrigeration cycle. It's just now we're moving energy from a water stream to another water stream. Then that secondary condenser water stream is pumped out to a cooling tower or a fluid cooler that is located outside. We still have a device that's outside. It's just that is now our cooling tower instead of our chiller. And that is where our heat rejection ultimately is going to happen. Here's another one of my sketches, but you're quickly going to realize there's a lot more going on with this system. We, we have our water source chiller, which is inside the building. We have our chilled water pump, which is sending out 45-degree water, going out to the chilled water cooling coils, coming back a little bit warmer, goes through the chiller where we chill the water down, and then it sends it back out. On this side of the system, everything is identical compared to an air source chiller. Fundamentally, there's nothing different about this side of the process. But our water source chiller, we're pulling heat out of our warmish chilled water and then using a DX refrigeration process to move that heat into this water stream on this side. We have to have another pump because that water is not going to move on its own. So we have a condenser water pump that's moving the condenser water loop on this side of our chiller. Our condenser return, which you can see is moving towards the cooling tower over here. So that is at about 90 degrees. So comparatively, that's a lot warmer than what's going on our chilled water side. So we're sending 90-degree water to our cooling tower or fluid cooler. You can see we have a third pump over here and a little basin filled with water inside this tower. And this pump is taking water from the basin, pumping it up through some spray nozzles. And it's basically misting water over this coil that's in here. So we're sending our water in here, and you can see this water has multiple passes through the cooling tower as we are spraying it with this basin water. And then we're also running this fan at the top. As we run this fan, this is pushing air out the top, or maybe the side, depending on how it's configured, which will pull in air through some openings in the side here. So as the fan runs, we're pulling air in through the side, which is also going to help with heat transfer. We have our pump here circulating the sump water. So this is pulling water out of the basin, pushing it through these spray nozzles, which mists over the coils, ends up back in the basin. So that's kind of its own little mini loop on this side. And our water comes back cooler than what we sent it at. So if we were sending it in at 90 degrees, ran it through this cooling tower, and then it comes back colder, and then just starts over again. So this side of the system is constantly going between 45 degree water out, 55 degree water in, and then this side 90 degree water out, 80 degree water in, and both sides kind of have their own loop, but they are working together. We're just taking energy from this, well, energy from the coils ultimately, moving that into the condenser water stream, and then ultimately rejecting that heat to the outside. So you can see there's a lot of stuff going on here, significantly more complicated than a basic air source chiller system. So to recap some of that, the condenser water energy, that's getting released by running air through the sump water, and that water, some of it gets evaporated into the air as it's absorbing that heat energy from the condenser water. What's unique about this setup is the heat transfer of the cooling tower is driven by the outside air wet bulb temperature and not the dry bulb temperature. On an air source chiller, it's all about the dry bulb temperature. In a water source chiller with a cooling tower, wet bulb temperature is what's driving this. The reason being, if we have a lower wet bulb temperature, that means our air is drier, which means we're going to have better heat transfer through that evaporation process at the tower. To put it in another phrase, the drier air, if we have a lower wet bulb temperature, that's going to be more able to accept the water. And this does add a second heat transfer step. We have our water to water heat transfer process at the chiller, and then we have our water to air heat transfer process at the cooling tower. Significantly more complicated. We have a lot more moving parts, more equipment to maintain. There can also be water treatment requirements. One other thing I didn't list here is the basin water in the cooling tower. What if you live in a climate where you have to be worried about freeze protection issues? In the winter, is that water in the tower going to freeze? And if it is, like in Spokane, we would have to figure out what to do about that. One method is you just drain the tower every winter, and then you just don't have cooling. But maybe that's fine. A lot of times we don't need any cooling in the winter anyway, so no big deal. Another way to do it is at the bottom of the basin, you stick in some electric resistance heaters that will keep that sump water at a minimum temperature, keep it from freezing. But the downside of having those heaters is, well, one, that's going to use energy. Even though you're not using the chilled water system, now you have to run these heaters for freeze protection. And two, you have to make sure that those heaters stay working. If you don't realize that those heaters failed, well, now you're back to having a freeze protection problem. At a more macro level, this is essentially what this would look like. We have our cooling tower or fluid cooler up on the roof somewhere. The orange and yellow pipes here would represent our condenser supply and return. In this case, the chiller's down in the basement, but you can see on this side we have condenser water piping. On this side we have chilled water piping, and so the heat transfer would be going from one stream to the other. And then we have chilled water supply going up to some air handlers with chilled water coils. This seems like a long way to go for your piping, going from the roof down to the basement, up to the roof again. That's probably not how most of these projects would be designed. More likely there'd be multiple air handlers throughout the building, maybe one air handler per floor or something like that. But fundamentally, that's how this system is configured. We're going to come back to this idea of approach, which we talked about quite a bit during the heat pump lecture. Cooling tower fans. I mentioned that the cooling tower has this big fan that's moving air through that coil. That cooling tower fan, typically they're either on or off, meaning it'll cycle on to 100% speed, and then when it reaches whatever set point you set, it'll turn off. And then the water will get warmer and warmer and warmer until it kicks it on again, and that'll cool it down, and then it'll turn off again. So that would be a cycling fan. It's not great control. It leads to a lot more fluctuations in temperature because you're constantly overshooting and undershooting your set point, but that's how some of these fans are designed to operate. Or commonly they're two-speed fans. You can have a low speed and a high speed. So maybe you can run at low speed for a while, but then once you start to get out of set point, you bump it to high speed until it's under control, and then you bump back to low speed. So that would give you much less fluctuations around your set point. Or the best option would be to control it with a VFD and actually control the fan speed to whatever you need. So if you only need 70%, then you run that fan at 70% fan speed. Our cooling tower fan usage. So how much energy that fan is going to use is going to depend on our active operating conditions, which really comes down to two primary variables. We're going to have our current cooling load in the building. So if we have a high load, if we need a lot of cooling, that will lead to a high fan speed because we need more heat rejection. Or if it's not VFD controlled, maybe that just means it's going to have a high cycling rate. So it's cycling on 80% of the time, and then it's off 20% of the time. Conversely, if we have a low load, that'll be a low fan speed or a low cycling because we don't need as much heat rejection. The fan speed or cycling is going to approximately track with the cooling load, assuming some constant wet bulb temperature. I'm going to come back to that idea of the wet bulb temperature and the impact that has. But for the same wet bulb temperature, if you have about a 60% load in your building, your fan is probably running at about 60% speed or cycling on 60% of the time. That's variable one. The second variable is the current outside wet bulb temperature, which I already mentioned earlier. If we have a high wet bulb temperature, it's going to lead to a high fan speed or cycling because it's harder to evaporate the water. If we have a low wet bulb temperature, it'll mean a low fan speed because it's easier to evaporate the water. But what if we're in this scenario where our cooling load is low, which is good for energy use because that means our fan doesn't have to work as hard, but our wet bulb temperature is high, which is bad for energy use. So these factors are working against each other. One is good, one is bad. What's the resultant outcome there? So that brings us a long way around back to this idea of approach. So the condenser water supply wants to get as low as possible before going into our chiller, because the lower we can drive that temperature, that's going to maximize our heat transfer. If our condenser water supply into the chiller is low, that makes it easier for the chiller to move heat from the chilled water stream to the condenser water stream. The supply would reach the wet bulb temperature in an ideal situation. So if our wet bulb temperature is 65 degrees Fahrenheit, ideally, in a perfect world, the condenser supply could also get down to 65, but it couldn't ever get any lower. But in the real world, that's not what happens. We can't quite get there. As an example, if our condenser supply is 80 degrees, which if you think back to that diagram I showed you, that's what I used in that example, I think. If our condenser supply is 80 and our wet bulb temperature is 65, our approach there is 15 degrees. We got within 15 degrees of ideal heat transfer. So a lower approach means we're approaching those idealized conditions. Same idea as approach when we're talking about an air conditioning system. The design approach, which I'm referencing that as a specific term, the design approach is the worst case condition based on the highest wet bulb temperature we can expect and our design condenser water supply temperature. As a design engineer, this is what I care about. What's my worst case condition? What is my design approach for my cooling tower? So our design approach is our design condenser supply temperature minus our maximum expected wet bulb temperature. That's the conditions the tower is designed to handle. Worst case scenario. The other term, though, is the available approach, which you could describe as how much approach do we have right now at this exact hour, at this current condition. And that's going to be changing all over the place. So our available approach is going to be our condenser supply temperature minus our current wet bulb temperature. So our design approach, worst case condition. Available approach is what do we have right now? Then we have this term called the wet bulb approach factor, which is just your design approach divided by your available approach. Conceptually, your heads might be spinning a little bit, but bear with me. I'll have an example here in a sec that helps illustrate this. If we have more approach available, meaning we have a lower wet bulb temperature, that means our tower fan doesn't need to work as hard. Conversely, if we have less approach available, our fan needs to work harder. So now our cooling tower fan, either cycling or our speed percent, could be defined as our fan cycling percent, if we have a cycling fan, would be our cooling load percent, because we know that our fan cycling will be equal to or rather proportional to our cooling load, multiplied by this wet bulb approach factor. If we have a VFD controlled fan, it's the same equation. It's just instead of how much it's cycling on, this is the fan speed at which it's going to run. With these equations, now we can account for both the cooling load and the wet bulb temperature to determine how often our fan is cycling or what speed percent we need to run the fan at. So now we have both variables that we can use. So we can scale our fan energy with our cooling load, and we can scale it with our wet bulb temperature. So we'll get a fan energy bonus for those lower wet bulb temps and a penalty for the higher wet bulb temps. Quick example. Let's say we have a cooling tower that's designed for a 63-degree wet bulb temperature with a condenser supply of 80 degrees. So that is the worst case condition. That's what we're designed for. Let's say we look at a moment in time where our cooling load is 50%. All of our chilled water systems are running at 50%, and it just so happens to be 63 degrees wet bulb right now, same as our design. Our wet bulb approach factor is going to be 1.0 because it's operating at the design temperature. So our cooling tower fan would have to cycle on 50% of the time or run at 50% fan speed because we have 50% load and we have a 1.0 wet bulb approach factor. But what if the next day it was at 53-degree wet bulb, which means we have more available approach? Our new approach factor would be our design delta, 80-degree supply minus 63-degree wet bulb, divided by what our available approach is today, 80 minus 58, and we come up with this factor of 0.773. So what would our fan cycling be now? 50% load times that 0.773 approach factor. So now it only needs to cycle on about 39% of the time. And so you can see how if we have more available approach, that's going to lead to less cycling of the fan or a lower fan speed, and vice versa. You could have a freak day where maybe we designed it for 63-degree wet bulb, but we have a day where we're at 67. And that will make our wet bulb approach factor greater than 1. And now it's going to have to work even harder. So because we have more available approach, conditions are better, the fan doesn't have to work as hard. And you can, if you're thinking ahead what this bin calculation might look like, you can probably see what you're going to have to do. You're going to have to figure out, well, how much energy am I going to use at each bin condition based on the active wet bulb temperature. So if water source chillers with a cooling tower, I mentioned they're so much more complicated. There's all these extra parts and pieces. You have this big cooling tower, you have water treatment you have to worry about, you have more pumps that you have to maintain. Why would we want to use water source chillers instead of an air source chiller? And the answer is they are more efficient systems. Water is a much better heat transfer medium than air. Pound for pound, it's about 4 to 5 times as much heat that you can transfer through water as opposed to through air. So we're adding this cooling tower, and that tower has a big fan on it, at least one extra pump, most likely 2 extra pumps. That added energy for those systems is offset by improved efficiency of the chiller. So we have a reduced kilowatts per ton at the chiller, but we are adding energy at the cooling tower and some additional pumps. But ultimately, it works out that these are more efficient systems in the end. And is that worth the effort? Depends on a number of things. Depends on your client. What are your electric rates? How much cooling load are you dealing with? If you have an 80-ton chiller, that would be a pretty small chilled water system. Putting in a water source chiller with a cooling tower, that probably doesn't make a lot of sense. But if you have a big 1,000-ton chiller, it's moving all kinds of energy, maybe that would be worth it to maintain that extra equipment. It'd be especially worth it if you live somewhere where you have really high electric rates. But if you live somewhere like in Washington, where we have very low electric rates, you're probably not going to see a lot of cooling towers. And I can tell you, we don't see a lot of cooling towers in Washington. So let's talk about lift, which is another concept we're piggybacking from back when we talked about heat pumps. If we're going to save energy at our chiller, we can reduce the lift of the chiller. And what the lift is the temperature difference between the refrigerant in the condenser and evaporator sections of the DX cooling process. I'll have a refrigerant graph here in a moment, but remember the refrigerant process is a somewhat rectangular process on the pressure enthalpy chart. And the high line that's running horizontal, that's our condenser temperature, and the low line running horizontal is our evaporator temperature. So the lift is just the temperature difference between the hot side and the cold side of our refrigerant process. And that lift is ultimately the work that the compressor is doing. Because remember, the compressor is the device that makes this whole thing work with the refrigerant, and the lift is that compressor work. If you have a very high delta T, which would be a very high lift, that means your compressor is doing a lot of work. As a reminder, condenser, that's where we're dumping the heat. So that would be our high refrigerant temperature and pressure. The evaporator is where we're absorbing the heat. So that would be the low refrigerant temperature. For an air source chiller, the evaporator section is our chilled water. That's our heat source. That's where we're pulling heat from. And the condenser section is our outside ambient air. That's our heat sink. For a water source chiller, the evaporator section is still the chilled water. Again, the chilled water side of the system fundamentally doesn't change based on these two approaches to a chilled water system. But the condenser section would be our condenser water, because that's where we're dumping the heat sink, or that's where we're dumping heat as our heat sink. Looking back at a pressure enthalpy diagram, recall this is the general process of a refrigerant. Evaporator section is our low temperature. Condenser section is our high temperature. The delta, that is our lift. And that's what this compressor is doing. If you have a water source chiller with a cooling tower, what if we could lower the condenser water temperature? Then it would be easier for the chiller to dump heat into the water. I mentioned that earlier when I was talking about approach. Or if we can raise the chilled water supply temperature, then it's easier for the chiller to absorb heat from the water, which is also good. So both of these scenarios would reduce the required lift of the chiller. Or we could do both, save energy on both ends of this equation. So fundamentally, what I'm talking about is if we're able to adjust the conditions that'll change the temperatures at which we need to run our refrigerant system, we can do that to reduce the lift. For an air source chiller, the condenser temperature is set by the current outside air temperature. And there isn't much we can do to change that until we invent a weather machine. If it's 100 degrees outside, that is our condenser temperature on the refrigerant side, and we can't change that. Nothing we can do. But we still can change the chilled water supply temperature to reduce lift and save energy on the evaporator side. And I think I'll have some slides here that should help illustrate that. For either case, whether it's air source or water source, we can save about 1 to 1.5% of chiller power for each degree Fahrenheit we can reduce the lift. And that is per degree on either side, whether that's the condenser temperature or the evaporator temperature. And that would be effectively a 1 to 1.5% reduction on the kW per ton of the chiller. Back to these diagrams. If we could raise the chilled water set point, that is effectively raising the evaporator side of this process, because the evaporator side is on the chilled water side. And if we can raise that refrigerant evaporator temperature, that reduces the amount of lift. Or if we can lower the condenser water set point, that would be a reduction in the condenser side of the refrigerant. And I totally get it can be a little confusing talking about the condenser side of the refrigerant versus the condenser water of the chilled water system. That can be a little confusing. So try to keep those terms straight. But if we can lower the condenser water set point, that reduces lift on the high side, ultimately reduces the lift of our compressor. Or maybe we do both. If we can lower the condenser water, raise the chilled water set point, we can attack it from both ends. Last few slides to kind of sum things up. What are some energy saving measures we can do for chilled water systems? We can do a chiller replacement. That's probably the simplest measure you can do. You have an old inefficient chiller, you tear it out, you put in a new, more efficient chiller. That'll reduce your kW per ton, which ultimately improves your efficiency, gives you energy savings. Or you could take an air source system and convert it to a water source system. So let's tear out an old air source chiller, put in a water source chiller, because I just explained that a water source chilled water system is going to be more efficient. The things you need to watch out for, though, does the customer want that maintenance? You're putting a lot on the customer's plate to maintain all of that equipment. And do they want to take that on? Do they have a properly trained maintenance staff to take care of that? You need to figure out how difficult is it going to be to reconfigure the chilled water piping. An air source chiller sits outside of the building. If you go to a water source chiller, you need to move that chiller inside and reconfigure the piping. How difficult is that going to be? It could be simple, or it could be a really substantial Cost. Is there even room indoors for a chiller? Chillers can take up a ton of space. So you might not have room anywhere to stick that thing inside your building. If you're putting something up on the roof, can your roof support a cooling tower from a structural standpoint? In that case, you would work with a structural engineer to figure out what kind of modifications need to be made to the structure of the building to make sure they can support this big new piece of equipment. So an air source to a water source conversion can be done, but it can very quickly get very complicated. You could convert your cooling tower fan to a VFD controlled, add a VFD to provide speed control. So you install a VFD on the cooling tower fan. Most older towers either cycle on and off, or they use 2-speed fans. And so a cooling tower fan VFD could save a lot of energy. These fans could have, or I should say often have, a pretty large horsepower requirement. And the larger the horsepower of the fan, the better candidate it's going to be for a VFD retrofit. The things to watch out for: you do need to replace the motor with an inverter duty motor, because that's true of any VFD retrofit. And you're going to have some potential controls implications for varying that speed. You'll need to have a control system that knows how to ramp the fan speed up and down. And last slide for you, then I can let you go. You could try and raise the chilled water supply set point. As we just discussed, that'll reduce the lift on the compressor, give you better efficiency by reducing the kW per ton. You can try to decrease your condenser water set point, same idea. Also going to reduce lift. But the thing you need to watch out for, anytime you're changing these set points, you can't just go in and say, well, you're supplying your chilled water at 45 degrees. We're just going to raise that to 50. You can't just do that. If all of your coils are sized for 45-degree water, they might not be able to cool properly with 50-degree water. If you have warmer, chilled water, that means you have less cooling capacity. And the same thing occurs on the condenser water side. Changing these set points messes with the cooling capacity of the system. So we need a smarter way to do this without compromising comfort. And down the road, when we get to controls, we're going to talk more about how we can change set points like that in a smart way without messing with the comfort of the building and the occupants. Any questions on that?